back. This is our next lecture in the series dealing with light. And we kind of have some of the light basics out of the way. We know about wavelength and frequency, and we know the relationship between energy and light. We also know that light can act like a wave or light can act like a particle depending on the circumstance. Well, today we kind of want to approach the question, what's the relationship between light and atoms? Why are we talking about light in the first place? Well, we kind of have to we have to backtrack a little bit and tell a story first. And it works like this. Um, we know that the light that we see from the sun, light that we see from a light bulb, an incandescent light bulb is what we call white light. And we also know that that light can be separated into all the colors of the spectrum. And not all of the electromagnetic spectrum, but only the visible portion of the spectrum. And in fact, you can even do this with a CD. If you take a CD and just kind of hold it in the light, you can actually see the CD allows the light to be split into its different wavelengths. So let me show you a picture of that. So this is a picture of, I literally just picked up the first CD that I found on my desk, which happens to be a CD of fingerstyle blues guitar. Anyways, um, if you just if you hold the CD, and you can do this at home, hold the CD into the light source, you're going to see all these different colors. And literally, here's our red, yellow, orange, green, blue, violet. Here's all the Roy G. Biv colors. So all of those wavelengths or colors, and it doesn't really matter how you say that, wavelength or color, they kind of mean the same thing. They're all packaged in the light that's coming from the sun, the light that's coming from incandescent light bulbs, etc. It's already there. And scientists knew about this for a long, long time. In fact, one of the first things they would do is experiments with light. They would take some kind of light source over here, and through a series of essentially a couple different things to put in the experiment. The one thing you need is a prism. And the prism is a fancy piece of glass that allows the light to be separated. And you actually see all the different colors from 400 nanometers all the way out to 750 nanometers. Now, scientists call this what's known as a continuous spectrum because it shows every single wavelength of light from 400 to 750 nanometers. All right. Now, what was interesting is back in the 1800s, even 17 and 1800s, scientists were first able to separate matter for the first time. And what I mean by that is they were able to take the air. We know the air we breathe is kind of a hodgepodge mixture of different compounds. If you take a look at, just look up on the internet, what's in air, you're going to find a list of like 20 different things. Number one thing is nitrogen, then oxygen, a little bit of carbon dioxide, argon, depending where you live, methane. So scientists were able to separate those materials, compounds really, out for the first time. So they were able to separate the nitrogen out of the air. They were able to separate the oxygen out of the air. And they would do all kinds of experiments with it. And eventually they said, well, they started probing matter in different ways. Like, what if we put a lot of electricity through this material? And that's exactly what they did. So they did that with all types of materials, even gases. They would take a gas, put it inside a glass tube. Well, actually, they would have to do it the other way around. They take a glass tube, and glass is really easy to melt, and you kind of melt one end of a glass tube, hook the other end up to a vacuum pump, and pump out all the air that's inside there, seal it off, and then put back in a little bit of one particular compound, like hydrogen or helium or nitrogen or oxygen or whatever. And then you put a lot of electricity through it. And it turns out that when you put a lot of electricity through a certain gas, it will actually give off light. So let's show you a picture of that. So this is what's known as the hydrogen lamp, and this is what you would have seen literally if we were doing this in a classroom. And inside this glass tube here, and this is just kind of a close-up of, I just grabbed this picture off the internet, but this is the exact same machine that we have over here on the left. But so let me see if I can kind of blow this picture up, because it's actually, this is actually embedded. But anyways, inside this glass tube is nothing but hydrogen, and they put metal electrodes. They put a metal electrode here and a metal electrode on the other side, and they put a huge amount of electricity through it, and all of a sudden the gas glows. So it's important to point out that there's nothing inside this tube except a lot of hydrogen. So they put a positive charge here, they put a negative side in here, and the only thing inside here is hydrogen gas, H2, and lots of hydrogen gas molecules. It looks like there's like a line going through here. That's not a wire. That's this hydrogen gas actually giving off, whether we want to call it light, when you want to look at light as a photon, this hydrogen gas is giving off light. And this was one of the coolest things since, well, if you're in the 1800s, I don't know what's cool in the 1800s, but this is pretty cool. So obviously scientists are a pretty curious bunch, and they really want to explain this. Why is hydrogen doing this, right? Why is, if I take a gas like this and put a lot of electricity through it, why does it glow? And not just glow, but look at this thing. It's purple, right? It gives off purple light. Okay, now take this idea, and you've all probably seen neon lamps before. Hold on. So we've all seen neon lamps before, and it's nothing but a glass tube. Glass is so easy to bend. And they take all the air out of the glass tube, put only in one gas, like neon, and then put a lot of electricity through it. And sure enough, neon also gives off a specific color. But there's more. Everyone's seen fireworks before. If you take and put a specific type of atom into a firework and then blow the heck up, it will give off a very specific color. It's amazing. Now, some of these colors look a little bit skewed to my eye, but you could even do this with a penny. I think we talked about this in the last video. Go take a penny, put it in the stove, or maybe you already did that and you want to report back what you saw. Well, you put a penny in the stove. I'm not talking about putting it in the oven. I'm just talking about hold it with some tongs, not your fingers, and put it in the flame, and it should give off a little bit of a green flame. So scientists also knew that certain atoms gave off specific colors. So hopefully you're able to see what we're going on with. Obviously, there's some relationship here between atoms and light. And I know that was a terrible circle. I apologize. But so we got to find out, what's the mystery? Why are atoms giving off light? Okay? And why would hydrogen give off this purple light? Well, remember, scientists have a couple tricks up their sleeve. Scientists have prisms. They have things called spectroscopes. And this is the simplest example we showed with the CD. The CD can act as a prism to separate out the light. What if we take this light that's given off from something like hydrogen, and we then take this light, let me erase some of this. What if I take some of this light and instead pass this light through, let's just call this a P for prism, and then look at the light coming out of here. Prisms are things that allow us to separate light. Maybe there's one or more types of light actually given off inside here. So we'll pass this light through a prism, and then we'll kind of take a look on this end. There's our eyeball. That's a horrible eyeball. But then we'll take a look at this end, the light given off after this hydrogen light passes through a prism. Okay, and what's good is people did that. Okay, so if we were doing this in class, we would take one of these things. This is a rather inexpensive spectroscope. It's a device that allows us to separate light. And what you would do is you would look through this side. So I guess we're going to put your eyeball over here, all right? And maybe this is the Lord of the Rings eyeball. I don't know. I don't remember the eyeball for Sauron. But anyways, you're going to look through this side. And over here, you're going to put your light source. So let's say over here we have our hydrogen lamp, and it is giving off light in all directions. and let's say some of that light goes through here through the spectroscope. Now that light's going to pass through essentially our spectroscope inside here, which we can conclusively say magic happens. I'm just kidding. Scientists always love it when you say the word magic. Anyways, magic happens and the light is separated. So if you looked at something, not a hydrogen lamp, but if you look at something like the sun, and you'll see this. You'll see a continuous spectrum inside of here. Now you can buy one of these on your own. I'm sure you can get one for cheap. I mean, 10 bucks is as cheap as you can get. And you can see the spectrum of the sun. Okay, and it's a continuous spectrum. If you notice down here where there's numbers, there's a 4 over here and a 7. So that is for 400 nanometers and 700 nanometers. And these spectroscopes are great. If you look at the light coming from the sun, don't look at the sun directly. It's going to blind you. But you can see all the colors that are actually given off from the sun. Okay, so do this. But now don't put the sun in the way, put the hydrogen lamp in the way. And instead you see something like this. So let's say we have a hydrogen lamp and this light is passing into whether you call it a prism or a spectroscope or diffraction grating, whatever the term is, it doesn't matter. Something that's able to separate the light. So that it turns out we do not get a continuous spectrum like you would see if you looked at the light coming from the sun. Instead, we see something very different. This purple light that's given off by the hydrogen instead gives us 4 individual, there's 1, 2, 3, 4 individual colors. So that, how do I say this? That purple color that we see, I don't know, can you see this over here? That purple color, the purple is really the sum of these 4 individual colors. So it may be kind of a stretch to believe that all 4 of these colors together sum to give you purple. Now, if you have any experience in music, if you play piano or if you play guitar, those are 2 instruments where you can play something called a chord. And a chord is nothing more than, at minimum, 3 notes played together at exactly the same time. Like if I wanted to play an A chord, I would play these 3 notes exactly together at the same time. I would play A, oh darn it, then E, I think it's a C sharp. And if it's not a C sharp, forgive me. But anyways, you play these 3 notes together at exactly the same time, and they, I don't know how to say this, they sum together to give you something new. They don't sound like an individual note. It doesn't sound like an A note. It sounds like the sum of these 3 notes. So go find a piano and play these 3 notes together and you get an A chord or a guitar. And if you're playing this in a band, let's say you're playing an instrument like a trumpet, you can't play all 3 notes at the same time, but maybe all 3 of the different trumpet players are playing 3 different notes, which together sound like a chord. So let's sum this up. The purple light, and maybe I got to write it up here, the purple light given off by hydrogen, as hydrogen is excited. And the term you want to use here is excited, excited. That's what happens when an atom is given a huge amount of energy, like passing a lot of electricity through it. When hydrogen is excited and that light is passed through a prism, it turns out that light is a result of the sum of 4 individual colors. So we can say these 4 colors are 4 individual wavelengths. And this basically blew people's minds. Right? If this is the person's mind, there's their nose, like literally there's fire coming out of it, because it blew people's minds that an element like hydrogen would give off these 4 individual colors. So this is basically like insert thought bubble question mark. Why is this occurring? Right? Why does this occur? And a long time people could not explain why this occurs. Let me just show you a different picture of the same thing. So take your hydrogen light source. Whoop, got to change colors. Take your hydrogen lamp, pass it through a series of slits, prism, and you get this exact same thing. All right, and here's an example of how you should look through one of these spectroscopes. So by the way, I don't know how you're going to find a hydrogen lamp out there. You can certainly get a spectroscope, But okay, so this was like the problem of um, the problem of the early 20th century. People could not figure out why atoms were giving off light, and they looked at this with all kinds of atoms. They then looked at atoms. If they saw this with hydrogen, then like, hey, what if does nitrogen do this? Does helium do this? Does argon do this? And if you go on Google and type in the spectrum of each of any atom, like maybe carbon dioxide, maybe neon, you see these individual spectral, what they're called spectral lines. I'm going to write that down. Spectral lines. You see spectral lines for every single element. Now, what's interesting is I'm going to kind of get to the conclusion of this pretty soon, but these spectral lines are unique to the particular element. All right, so just kind of pause for a moment. Spectral line is unique to an element or compound. So if I saw a series of spectral lines, I could actually work back and figure out exactly what element was giving off that particular light. Now, this is really useful because none of us can go to the sun, but we can take obviously you can't do this with the $10 spectroscope, but with a really fancy spectroscope, you can look at the light given off by the sun and figure out, well, there's a lot of spectral lines in there. We can figure out exactly what elements are present in the sun based off the spectral lines that it's giving off. So there is a huge field of study here. Astronomers can look at stars and they can figure out exactly the process of nuclear fusion that's occurring inside each one. So it's a huge deal. Okay, so let's get to the bottom of this. Well, we're not talking about Max Planck yet. So the real question is why? Why are hydrogen atoms doing this, right? You ready? Okay, so let's finish this. I chose this image just because it shows you exactly which specific wavelengths correspond to the hydrogen emission. So this is hydrogen emission. And it's important to point out this is hydrogen emission. These are the colors or wavelengths that are given off by hydrogen that we can see. So this is only the visible spectrum, okay? There might be other types of light given off in other parts of the spectrum, like infrared and ultraviolet. That doesn't look like a U. That looks better like a U. So not just we know today that there are different wavelengths of light given off by hydrogen in the infrared and ultraviolet spectrum. So obviously I can't show you that because we don't have the classroom, but there it is. So there's something funny about these 4 individual wavelengths. Why would hydrogen do this? So let's think about hydrogen right now. Kind of theorize. Hydrogen is a very simple atom. It's got a nucleus, which basically means it's got a +1 charge here. It's got a proton in the nucleus. And it's got a shell, right? So this is a shell, and it's got 1 electron in the shell. So we've got a proton here, and we've got an electron here, and that's it for hydrogen. Obviously, the most common isotope for hydrogen has 0 neutrons, so this is the most likely case. So why would hydrogen do this? So in order to get hydrogen to give off light, you have to add energy. So somehow over here, we are going to add a huge amount of energy to hydrogen. And after hydrogen has somehow absorbed, so hydrogen has to absorb. So hydrogen has to absorb energy. So somehow, we don't even know how the hydrogen atom can do that. But after hydrogen absorbs this energy from, in this case, we're going to use electricity. Afterwards, the hydrogen atom has to somehow release light. Okay? And these 4 wavelengths of light are the light that's being released by hydrogen after it has absorbed energy and then released energy. So Hydrogen absorbs energy from the electricity and it releases energy in the form of light. So this is a really important conclusion. It is absorbing energy and it is releasing energy, but it's releasing energy in a different form. It's releasing the energy in the form of light, all right? And if you have questions on this, ask. At any point in the lecture, you feel like there's a question, you don't understand something, pause it, write down the question, and then ask me. People have been doing that. Not many people, but people have been. I have people all the time that are asking me questions at all hours of the day, literally. When they watch a video and they don't understand what's going on, they're thinking about it. And so we're just kind of approaching this logically. If an atom absorbs energy somehow, one way it can absorb energy is by electricity. It somehow is able to release that energy again, but it does so in the form of light. So the question is how? How is a hydrogen atom going to do this? Okay, and people couldn't figure this out for a long time, but along comes this person. Let me pause and find this person. Boom, there he is. This person is known as Niels Bohr, and let's not write this on his forehead. Let's write this over here, Niels, and I think I'm spelling it right. There's an I right here. That doesn't look like Mel. Oh, it does look like Mel's, but this is Niels Bohr. And Niels Bohr is kind of, let's put a thought bubble. No, it's not thought bubble, it's not his name. His thought bubble is this. Let's put another thought bubble. His question mark is, why does hydrogen do this? Now, I don't mean to make Niels Bohr look like a devil here somehow, so let's erase this. But Niels Bohr is thinking about, why does hydrogen do this? So the key here is the atoms, the hydrogen atoms are being excited and absorbing energy. So that was the idea that we talked about before. Atoms get excited and they absorb energy. Atoms get excited and they absorb energy, and then they release energy in the form of light. So how is an atom going to absorb energy? So here's the question. How can an atom absorb energy? You want to know what Niels Bohr found? It's this. So what we're going to do is draw some shells for an atom. And, whoop, not yellow. I don't want to use yellow. Yellow bad. Let's use this color. So let's say here's an atom. Oh, by the way, before Niels Bohr came along, we didn't know about shells. Aha. So let's say we've got an atom, and here's the nucleus. So there's our proton, and here's our electron. Niels Bohr realized that electrons have, well, one way to look at this is this. I think we've talked about this before, but this proton is positively charged, and this electron is negatively charged. And in physics, and you all took physics, you know that opposite charges have an attractive force together. Now, there's two ways you can look at this. And believe me, I'm not trying to overwhelm you right now with math. I just want you to think about it. We know that the electrical force is going to be equal to a constant K times Q1 times Q2 divided by R squared. Now, R is basically how far these things are apart. Q1 and Q2 is how big this positive and negative charge are. Now, if you plug in, I don't care about the actual number, but the most important thing is that this charge is positive and this charge is negative. Now, when you're all said and done, you're going to end up with a force. But the thing is, the force is going to be negative. What does negative mean in force? Negative means attraction. Okay? Now, we talked about this when you talked about gravity. Gravity is attractive. The acceleration of gravity is negative 9.81 meters per second squared because it is attractive. So this positive nucleus is attracting this negative electron. So there's no secret there. That's kind of old news. But along with force, there's also an energy. And usually the energy equation is written like this. For some reason, they use U for energy. I don't know why, but I'm using U right now. U just means energy. Along with an attractive force, all right? Along with an attractive force, and that's the force that keeps the electron held to the nucleus. There's also an attractive energy. And the energy equation looks like this. U equals K, Q1, Q2. So far it looks exactly the same as this, but it's just divided by R. So our analogy that we used above is the same. We have a positive times a negative. So in the end of the day, our energy is negative. Negative just means attractive. So far, so good? So one conclusion we can make is there is an attractive energy holding this electron to the nucleus. So far, so good? Okay, how do we get back to answering our original question? How can an atom absorb energy? Well, what Niels Bohr realized is an atom can absorb energy by the electron literally moving farther away from the nucleus to another shell. So somewhere out here, there is another shell that's going around the atom. So let's erase some of this information. So what Niels Bohr realized is when an atom absorbs energy, it will actually move farther away from the nucleus. So the first step is absorb energy. And the second step that happens is electron moves farther away. So what Niels Bohr realized is that the way atoms absorb energy is by electrons moving farther away from the nucleus. So we realize that this is the whole idea for electron shells comes in. So this is the first shell. This is the second shell. And atoms can actually have a huge number of shells. And the shell that the electron jumps to, it depends on how much energy absorbed in the first place. So if the atom absorbs, let's say an atom absorbs a lot of energy, okay, then the electron can jump from here, let's say all the way out to here. Actually, I don't want to draw the arrow on top of that arrow. Let's say the electron can jump from here all the way out to here, to a shell that's right here. So if an atom absorbs a huge amount of energy, the electron can jump really far away. So let's say this is the first shell, this is the second shell, this is the third shell, all right? Now, if the electron's all the way out here now, it's still being attracted to the nucleus because it's still negative and the proton's still positive. Now, what that means is because it's farther away, this distance from, let's say, from here to here, that distance, r, is larger. Now, what this means is the attractive energy, U, is a little bit lower. And remember, U is equal to, it's proportional to 1 over the distance. So the farther the electron gets away, the energy of this electron becomes lower. Okay, so what we learned is what Niels Bohr discovered is that atoms can absorb energy by electrons moving farther away from the nucleus. Okay, now this isn't the end of the story. Electrons don't stay here forever. In fact, you remember the second part of our problem that we came up with before. Atoms have to, where was that? Oh, I forgot where we put that now. But atoms basically have to absorb energy, and then they have to release the energy. So this is the first part. Atoms absorb energy by electrons moving farther away. But where does the light come from? Okay, here's the next part. Okay, so how does an atom release energy? So we know that let's get back to drawing, our proton is here, and electron was here. So this is kind of like home. This first shell is kind of like home for the electron. It's the place where the electron is the closest to the nucleus, and because this distance here between the nucleus and this electron is the smallest, the energy here is largest. There's the most attractive energy holding the electron to the nucleus. But the electron, let's say, has jumped really far away from the nucleus as it's absorbed energy. So this is all described out here. So here the energy is largest, here the energy is lower. All right, but now we haven't gotten to the part where how does an atom release energy? We know an atom is going to release energy by giving off light. So the electron doesn't stay out here forever. So we're going to add this little note. The electron doesn't stay out here forever. Wherever the electron has jumped to, whether the electron has jumped to the second shell, the third shell, the fifth shell, the seventh shell, wherever the electrons jump to, it doesn't stay. It turns out the electron, let's say the electron, I'm just going to draw it over here. What happens is this. the electron will drop back closer to the nucleus. So let's say, for example, the electron goes from the third shell back to the second shell. So in this process, when the electron drops back to the nucleus, that is the process which releases, that's our light being given off. So when atoms give off a color, whether it's in a firework or it's in a hydrogen lamp, the light that's being released occurs when the electron drops back closer to the nucleus. And that's a really important conclusion. Okay, so I wrote this down just to kind of have it as a note. So this is the way that atoms release energy after they absorb it. Electrons drop closer to the nucleus. Now I know I have it going from the third shell to the second shell. Why doesn't it go all the way back down to the first? Well, it can. Here's the next conclusion. The light, or rather, the energy that's being released, the type of light being released, is proportional to how far it jumps. It turns out that electrons that transition all the way back to the nucleus or to the first shell rather, give off the highest energy of light. And electrons that transition back to farther away from the nucleus give off lower energy light. For example, this light that's being released when an electron in a hydrogen atom goes from the third shell to the second shell, the light being released will happen to be in the visible spectrum. Okay, so let's just kind of summarize this. Atoms absorb energy by electrons moving farther away from the nucleus. And then they give off light when the electron drops back closer to the nucleus, right? Now, you could spend a week in a college level course just talking about this entire process. We don't have that time, and we are not going to go into that great detail. You might have a lot of questions. Why does it go from the third to the second? Why doesn't it go from third all the way back? Well, there's a lot of cases, there's a lot of probability here. There's a lot of what if. It turns out it can just go from the third to the second, and then the second to the first. Or it can go from the third to the first, or the fifth to the first, or the fifth to the third. All of those cases actually exist. So the next question we want to answer is this. I'm going to go back to this slide. Why? So this is our next question in order. Why these wavelengths? Whenever hydrogen is excited, these are the only 4 visible colors that are given off. It's not random. It doesn't change. The next time you turn on the hydrogen lamp, this wavelength doesn't become a different wavelength, right? It's always these 4 wavelengths. So why? How does our model of the atom, which we just figured out here, how does this explain why these 4 wavelengths occur? Okay, for here, we have to go into a little bit of math. Okay, so in order to figure out the next part, we're going to have to do a little bit of math. And here's what I'm going to do. Instead of taking these shells as rings, so instead of drawing, if I had to draw a shell there, let's say a shell here, and we kind of move this over, move it over, move it over, move it over, and we'll draw one more. Instead of doing kind of a 3-dimensional thing, or 2-dimensional at least, where we're showing the shells, let's actually just show, let's show like this segment of the shells, right? Let's just show the shell from here to here to here, because then it just kind of looks like straight lines. So what I mean by that is let's turn it from this into something like this. And then instead of kind of doing it from here, you know what, let's make it a little bit simpler. Instead of doing it from here, let's rotate it up. So we're doing the section from here up. We're going from the shell closest to the nucleus, and we're working away. So this is first shell, second shell, third shell. So let me redraw that the way I'm kind of hoping you can see it. So what I've done is this, and these represent, let's say, 5 of the shells for a hydrogen atom. Proton's all the way down here. This would be where the electron spends most of its time in the first shell. And again, instead of drawing circles, I'll just draw these lines. It's a little bit easier. So we know that an atom absorbs energy. This electron will move farther away from the nucleus. So let's say this electron will jump up to here, and will stay there for a little bit of time, and let's say it can jump back down. And we're talking about the case where it drops back down to the second shell. So that's our hypothetical. Well, how do we go back to get those specific wavelengths of color as was shown in the previous slide? We got to do a little bit of math. Now, if you remember, electrons in shells have a specific energy, and the equation for energy is this. So this is the equation for the energy for an electron in a given shell. Let me write that down. So the equation is this. So we're going to use U because we used that for energy before. This is attractive energy. So because it is attractive, that's a plus minus energy. The energy is going to have, the equation is going to have a negative in front of it. Now I'm going to do this. I'm going to write this equation two ways. The first way is using a unit of energy we haven't talked about yet. It's called the electron volt. But then I'm going to show you the other way. And I'm not going to show you how to convert it right now, but I'm just going to write the equation. So the equation works like this, negative 13.6 EV. EV is a specific unit of energy called an electron volt. But I'm going to write this equation another way, and that's what we're going to use. So it's negative 13.6 EV divided by n squared, where n is equal to the number of the shell. So if we're talking about this very first shell down here, then we would just put, by the way, these numbers equals n. So n for this shell is 1, n for this shell is 2, n for this shell is 3, n for this shell is 4, n for this shell is 5, okay? So if I wanted to find out the energy of let's say I have an electron that would go into each of these shells, I can use this equation to find this energy. Just plug in negative 13.6 divided by the shell that it's in squared. Now, because EV, or electron volts, that's actually a unit of energy that we haven't talked about yet. So I'm going to turn this equation over into joules. So if I rewrite this, the same equation, but in joules, it's equal to negative 2.18 times 10 to the negative 19. And this time the unit will be in joules divided by n squared. So this is the equation we're going to use kind of right now, okay? And then later we'll come back to using this equation. We'll show you how to do conversions from joules to electron volts. So what I want to do right now is use this equation to find out how much energy the electron would have in each one of these 5 shells, okay? So I'm going to start with the shell all the way down here. By the way, the first shell is what also has a special name. It's what's known as the ground state. So if you are reading this in the book, you're going to be reading about the ground state, the first shell. So for the first shell, the energy the electron would have in here, n equals 1. If you plug 1 in here, you're basically going to get this. You're going to get, you just plug 1 squared in here, you're going to get U equals this. So let me do this. Let me rearrange this a little bit. Okay, so all I did is drag this over, so I have enough room to write the answers in here. So the energy for the first shell is equal to this. Energy for first shell is negative 2.18 times 10 to the negative 19 joules. So in other words, if the electron is in the first shell, it has this much attractive energy holding it to the nucleus. Okay, now let's do the second shell. The second shell, n equals 2. So if I plug n equals 2 in here, we got U equals negative 2.18 times 10 to the negative 19 joules divided by n squared. So 2 squared becomes 4. So the energy for this particular shell is going to be negative 5.45 times 10 to the negative 20 joules. Okay, so you could do the rest. If you plug in the 3 is going to turn into 3 squared is 9, 4 squared is 16, 5 squared is 25. So let me do this. Let me plug in these next 3 energies. Okay, so I just went and calculated the energy for all 5 shells. They're all negative. They're all going from the least amount of energy at the top to the most at the bottom. So the energy, what this just means is because this number is the biggest, and believe it or not, this number is larger than this one. This number is larger here. It's just saying that the electron is more attracted to the nucleus here than it is here. The farther the electron is away, the weaker it is attracted to the nucleus. Okay, so we got to get to the bottom of this. Where is the wavelength coming from? How is an atom, when it releases energy, giving off light? It comes from here. Niels Bohr realized this. He realized that the energy of the light or the wavelength of a light that's given off when an electron drops back closer to the nucleus is just equal to the difference in energy between two shells. So let's say this. Let's say an electron is going from the third shell and it is going back to the second shell. The energy, all right, get this, the energy of this light that's going to be given off. So this is a photon of light that's going to be given off when this transition happens is simply equal to the difference between these two shells. So let me show you that as an equation. Okay, so to wrap this up with an equation, here we go. If we want to know the energy of the photon that's going to be given off here, it's equal to the difference in energy from where it finishes. So we're taking the energy where it finishes minus the energy where it starts. So we need to take two energies. We're assuming a transition here between the third shell to the second shell. So we need to take these two energies and we're going to write them down on another page and subtract them. So the energy where we end up, 2. So we're taking this energy minus the energy where we started from 3 from here. All right, so let's do this on another page. Okay, so if we redo this equation, we're talking about a transition from the third shell to the second shell. So just putting the energies in, it's where we end up minus where we start. So E equals EF, which is going to be negative 5.45 times 10 to the negative 20 joules, minus, and I'm going to put this one in parentheses, a negative 2.42 times 10 to the negative 20. So the negative makes this a positive, and we end up with the energy of the photon that's being given off. It's still negative because it's attractive energy, but that's when we're talking about attractive energy from an electron to an atom, but the energy of the photon that's given off is going to be negative 3.03 times 10 to the negative 20 joules. Okay, now, it doesn't make sense to talk about the energies being negative for the photon, so whether we make this a negative or positive doesn't matter. But I want to know what's the wavelength. So come back to our equation we learned last time. E equals hc over lambda. But now I want to solve for wavelength. I know what this energy is. I want to solve for wavelength. So rearrange the equation. Lambda equals hc over E. So plug some numbers in. Plug in this number. It doesn't matter. Plug it in as a positive is the way to go. And what you end up with is this. So if you do the math, plug in hc and divide it by E, you end up with, let me get this off my calculator. So you end up with 0.0000656 meters. Okay, now, remember, when we talk about visible light, we want to turn it into nanometers. So this, in scientific notation, is 6.56 times 10 to the negative 1, 2, 3, 4, 5, 6. Or, if you put this into nanometers, it is 656 times 10 to the negative 9 meters, which is exactly the same as 656 nanometers. Okay, so 656 nanometers. Where have we seen that number before? Let us go back. Where have we seen 656 nanometers before? Wait for it, wait for it, wait for it. There. 656 nanometers is exactly equal to this wavelength. So what we just found is that when you look at the light being given off by hydrogen that's being excited with electricity, this red light that's being given off occurs because an electron goes from the third shell of a hydrogen atom back down to the second shell. When this electron transition, get that, electron transition occurs, this specific, there's the wavelength, this specific wavelength of light is given off. So what that means is these other three colors have to represent electron transitions from other shells. Now, what we know today is that this green light that's given off is a transition from the fourth shell to the second. This blue is fifth shell to the second, and this kind of purplish is from the sixth shell down to the second. In fact, all 4 colors of this light represent transitions back, all the way back to the second shell. Okay, don't believe it? Try it. Right? So this is a test. I'm not gonna solve this for you right now, but prove this. Prove using the equation we came up with before, only for the hydrogen atom, using the equation that this specific wavelength is given off with a transition from the 6th shell to the 2nd shell. All right, so solve it, and you'll be able to prove it. Okay, so this is the end of the lecture right now. Now I don't want to go longer. We're 45 minutes right now. It's a long lecture, but this is how we know that electrons are in shells in atoms. This is how atoms can give off light. Okay, so I'm going to give you some homework, probably 5 or 6 homework problems dealing with electron transitions in hydrogen, and then we'll take another quiz. All right, that's it. If you have questions, ask, ask, ask. All right, have a great day.